Okay, to get into the actual problem, again, I skip all the easy stuff and shoot straight to x prime is the thing I'm trying to show is inductive. I assume that a is in x prime, and I try to show that a plus 1 has the property that defines membership of x prime, namely that if I take any non-empty subset z of a plus 1, that this z must have an in-min element. So, taking this arbitrary non-empty subset of a plus 1, then it makes sense to me to branch this into two cases, one in which z is a subset of a and one in which a is an element of z. So notice that either a is in or not in z. So if a is not in z, we have this case. If it is in z, we have that case. Now, in the former case, we know that any non-empty subset of A has an in-min element, so that case is just done. In the other case, where A is an element of Z, then I again consider it, I consider branching into two separate cases. One in which, when I subtract out the set A, I get the empty set. That could be a possibility, is a possibility, and I'll deal with the other one in which that's non-empty afterwards. Now, if Z is equal to the set of A, then I argue that A itself must be an in-min element of Z. Well, for contradiction, suppose that Z has no in-min element, and in particular, there's only really one candidate for this A, so that means that A isn't in-min in Z. Well, given that, the very denial of the existence of an in-min element in Z is equivalent to there must be some element T in A that is also an element of Z, which is the set of A. But if T is in A, then, if T is in Z, then T is precisely equal to A, and on the previous page we assumed that T was in A, so we have that A is in A. Well, this just means that the set of A is itself a non-empty subset of A. Every non-empty subset of A, by assumption that A is in X prime, every non-empty subset of A has an in-min element. But notice, and this is, I'm doing so many references to previously stated things, but notice that this set A of just A just is Z. So we have established that both Z has an in-min element, and by the earlier assumption, it does not have an in-min element. There is our contradiction. So A is the in-min element of Z from way back when we made the first assumption for contradiction. Okay, we have one case left to consider. It is the case in which Z minus A, the set A, is not empty, in which case we can think about Z minus the set A, which now must be a subset of A, non-empty, and therefore has an in-min element. I claim that it should be easy to show that whatever that in-min element for Z minus A is, that it is an in-min element for just Z itself. And here the proof is complete.